I need to start this lecture out again with another explanation. This is a lecture that was recorded from a previous semester, uh, apologizing to everyone for the situation that we've been in. We've tried the best here to support your learning um, on this in this class, um, and I want to explain to you that the content of this lecture is a review of the second midterm, but there were some valuable things learned here, and so I think it's worth sharing it with you. The I'm going to share a portion of what's in here, which will make up the time for this class period. It goes back, and what it does is it reviews the integration of transformer, synchronous machine together. This lecture has some value in that it will solidify your understanding of how you analyze things together. So it's a little bit of a departure from what you're studying right now, which is the induction motors. I'm going to do a new lecture for your final lecture that I will record, or I will actually give the lecture live, that will go through the generation of speed torque curves for induction motors. That's the last thing that you need to know in this class. There's only a period of required, one class period required to get through that. But I want to present this information now as review. As I'm recording this actually right now, I'm not sure whether we will give this lecture before I record the final lecture and present it on induction motors or after. Let's talk about problem 2. Okay, so problem 2 is it says that you have, and I'm going to kind of highlight these problems. You've got to kind of look at what it's saying. Okay, the first thing is, when you give a rating of a machine, that usually means you're going to need it to do per-unitization. That's why. Okay, so there's a 25 megawatt synchronous generator. That's right here. And it supplies power to a remote community through a delta Y step-up transformer. It's going to be, when it says remote community, that means it's going to have probably a long distance line, and so typically they have a very high step-up transformer to 600 kV. And then you've got a very long 600 kV transmission line. Now I gave a rating under here for that transmission line. Everything's at 60 hertz. I'm highlighting the ratings. And then at the other end, there's a Y delta step down, which would be the remote substation here. And then I gave a per unit impedance for that transformer, a per unit impedance for the transformer by the synchronous generator, and then there's a per unit impedance for the transmission line given. And then a remote community is being fed, it says here, and it has a bulk load of 12 megawatts. So that's your load. It's got 0.8 power factor, but note also that the line-to-line voltage is 13.2 kV. It's not 13.8. So notice the transformer rating is 13.8, but the voltage is lower. And you got to pay attention to what is the voltage of the load first. And there's a sequence typically of solving these problems. So I state pretty clearly here, you've got 13.2 kV line to line, feeding a 12 MVA load, 0.8 lagging power factor. And then one of the students said I should label these. That would have maybe helped. So I did label them when I sent this out for everyone to do it the second time. So you have these three labels here. You got the point A, point B, and point C. So the remote community is being fed at point A. The first question asks, what's the line-to-line voltage at the sending end? That's point B, okay, of the delta Y step-up transformer. Now what we're going to need to do is we need to find a couple of things. The first thing is, number one, we need to find the load current, right? That's at the load end. We're going to have to solve, we're going to have to do a per phase line to neutral equivalent circuit. So basically, we need to determine the point of reference to solve the line to neutral circuit. Now, what do you think what do I mean by that? Does anybody know? By number 2? Anybody?
Figure out which point you would use to create the line of neutral circuit.
Yeah. So that means what? What does that mean, really? You know, I don't have any transformers in my line to neutral circuit, right?
Right.
That means I'm referring things to somewhere.
Right, so you're trying to determine where your main reference point is in comparison to your load and your feeding.
So what would it be? What do you think, based on what I'm asking for in A? What would that be?
That should be on the generator side.
No.
Or, no, excuse me, the load side, because everything is being fed to...
No, not the load either.
Really?
It says the sending end of the transmission line.
Oh, the sending end, so that would be our physical line.
We're finding it
connection.
Point B, right?
Yeah.
Everything should be solved in this region here. It should be solved in this region. Refer everything to there, because that's everything then can hinge off of that. That's why I gave you the rating of the transmission line. So once we find that, then that also tells you need to establish your base. Now, a lot of people got this right. They did their base correctly. So they actually did this, I'd say, intuitively, but then they didn't solve it correctly, which was a bit mind-boggling to me. So you establish the base. So the base that we're going to use is S equals 30 MVA, because that's the base of the transmission line. Its voltage, that'd be S base. The V base would be the voltage of that transmission line. Now you always do with three-phase circuits, your base is the line to neutral voltage. So it's going to be 600
everything's always given in line to line. You convert that to line to neutral. So that'd be 600 kV divided by square root of 3. And then you need to establish, ultimately you need a Z base. You don't really need an I base, but you can do this in one step. You could say Z base is equal to, I always have to think about this. So, right, P equals V squared over R, right? So if I rearrange this, R would be V squared over P. Okay, so that means, I always have to go back to Ohm's law to just make sure, because you can't remember everything. Z base, if I don't want to do an extra step, is simply going to be a V base squared divided by S base. I believe. Now it's a three-phase circuit, so it gets a little confusing, okay? So if you don't want to screw up, find I base. I base is going to be S base divided by 3 times V base. What happens when you go from here and here to here is you get some cancellations, and it's always confused me in three-phase, so I just don't do this, and then I say Z base is V base over I base, because I know that is correct. It's the per phase impedance of the base circuit. So that's your first step, and I'm going slowly. This is not really a long problem to solve if you know what to do. So what we're going to do is I'm going to find V base first by taking 600 kV, dividing it by square root of 3. And I get 346 kV. So that's my V base. Now the I base would be 30 e to the 6 divided by 3 and 346 e to the 3. So that's 30 e to the 6. So I'm going to calculate that. And I get to 28.9 amps. So the Z base would be, it's going to be a big number, okay? But that's because you have a very long transmission line too. It's because you have a very high voltage, not because you have a long transmission line. It's because you have a very high voltage and a low current, and that's what you want in a transmission line. So 346 kV divided by 28.9 amps will give me about 12 kilo ohms, or more exactly 11.97 kilo ohms. And I think a good portion of the class got this part right. Now, what are you going to do with this base? Well, you have a line to neutral circuit. This is the one part of the problem where you have to use the line to neutral circuit. So if you're going to reference everything, you're going to reference everything to the transmission line. Now, here's where a lot of people go wrong. You try to use turns ratio. So you try to do it the way we did it in chapter 2 with the single phase transformer. Turns ratios, you will get it wrong, I guarantee. There's a remote chance that you can do everything by saying, oh, I reference, so, Z prime is equal to N, say N 1 over N2, right? And they'll try to say, well, let's find the turns ratio. That is the wrong way to do it. You will make a mistake, I guarantee it. That's why I showed in the recorded lectures addendums, and I did it partially in class, but I did record this. But I think very few people watch this recording. Do not do that. For three-phase systems, there's a much, much easier way to do it, using the information that you've been given. So what you do, first of all, the easiest way to get things in the right reference is to use the base. It's the same thing. If you converted everything to per unit, or if you were given everything in per unit, and I said, I already did that. I said, these per unit references, they're referenced to the transmission line. So I already actually told you what your point of reference should be. So I already gave you and figured these out. To get those values in the first place, you might have had to do turns ratios and things like that. But I would never ask you to do that in a big problem like this. Okay, so at least on an exam. So what I'm going to do is I'm going to take these three impedances right here, and I'm going to multiply them times the base to get them in the right value. But why don't we write the circuit first? So the circuit is like this. At the load end, we have a voltage, and we have a current that we are going to find. It's a line current. In line to neutral circuits, you got to find the line current. Now this line to neutral voltage is on the 600 kV side of the transformer. This is where I'd say 90% of the class did this wrong, which is really discouraging to me to see that, okay? That's the very first thing you would have to do. Then you have your impedances that are going to string up. So, and actually I got to go back and do number 1 to get that line current, the load current. And what is this load current? This load current, just to show you, if we go in here, there's a load current that's going at point A that you could calculate from this information that was given. And then you need to move that load current over to the other side of the transformer. So let's find the load current. So the load current is the power of the load was 12 MVA. The line-to-line voltage is 13.2 kV. Hold on, stupid thing. I almost got it right. Okay, so we can find the load current. There was maybe 3 people who did this right, and then they did the voltage wrong. Okay, so the a lot of people got this correct. The load current was 524 amps. 524.9 amperes. Okay. Okay, so we did that, but now you've got to convert I load over, and this is where a lot of people did the wrong thing. Convert that load current to the other side of the transformer. Now, I showed this. You can go back I could even send an email out if anybody's interested and say this was the recorded lecture. It was actually an addendum to the last three-phase lecture. I showed why you can do this. The turns ratio, this is a voltage ratio. You just use that voltage ratio to get the current or the voltage. So if I'm trying to get current on the other side, I'm going to go up in voltage, so I know I'm going to go down in current. So that means it's quite clear to me that I'm going to say 13.8 divided by 600. That's the ratio that I'm going to ratio everything to. Now, the other thing is if I go down, this is also a phasor, see? So there's an angle to it. There's got to be an angle here. It's the power factor angle, because it doesn't matter whether you're a delta Y or a Y delta. If you do the line current going into the load with the power factor, and then you find the line current on the other side, you're going to preserve the power factor angle. There's not any shift. So essentially, we can find the the angle of the I load. So this was the magnitude here. The angle of the I load is going to be, it's negative because it's lagging, inverse cosine of 0.8, which is 36.9 degrees. Okay, so if we know then that this IL here going into the load is going to be 524.9 times 13.8 over 600. And then it's at an angle of negative 36.9 degrees. So what is that? That is, it actually ends up being around 12 amps. Here's where I think maybe 2 or 3 people got this right. If you got this right, you're pretty much home free if you do the voltage right. So that was, it's 12 amps. 12, negative 36.9. So now you think, what's the impedances on this line? Because what I'm going to do is I need to find the voltage at the other end of the line, the sending end. That's what I'm supposed to be finding. So there are 3 impedances. There's the impedance of this transformer. On the load side, there's impedance of the transmission line, and there's impedance of the feeder transformer. So that's, I'm trying to, now the, I said find it at the sending end, right? So I'm actually not going to worry about this. I'm only going to worry about these 2 things, these 2 impedances here to get to that one. And so I've got 2 impedances in series, the Z transformer 2 impedance and the Z line impedance. And I'm trying to find this voltage here. It's a line to neutral. Once I find that voltage, I just convert it the amplitude to line, and that's the answer. And then this current that's flowing through here is 12 minus 26.9 degrees. The only thing here is, what's this voltage? So it's the voltage that was on the 600 kV side of the transformer. We know that the voltage at the load was 13.2 kV. That's our reference point, our 0 reference point, because the power factor is defined at that point. And then I'm going to multiply this times 600 over 13.8. and divide by square root of 3.
Quick question on your notation because it's a little hard to see. Your
Yeah.
second ZL, is that ZL2? Or Z low?
ZT2.
Z2.
It should be
Okay.
whatever was up here. ZT2.
Oh, T2. Got it. Thank you.
Yeah, Z load, ZT2, ZT1. Okay, so I know what that is. So, cleaning up, okay, this is what I need to know. The voltage right here I need to know. That voltage is 13.2 kV times 600 divided by 13.8. So that's 573.9. So you can tell that, nominally I have a 600 kV system, but there's quite a bit of voltage droop, getting to the other end. Now this is the line to line, so divide that by square root of 3. Which I took 2 points off for not doing that, but I'm going to be taking more points off if people don't do this in the final, because it's just, you should know this by now. 331.3 kV, 0 degrees, okay? So that piece of information. The ZT2, I gave you a 0.08, J.08. So it's J.08 times the base value, that was 11.97 kiloohms. 0.08 times 11.97 e to the 3. And so that is 957.6 ohms. And then the transmission line was 0.07 plus J.2. Mostly reactive, mostly inductive, long line. That is going to be multiplied times 11.97 e to the 3. And so 0.07 times 11.97 e to the 3 is 837.9. I could just say 838 plus J so that's 2394. And so the Z total that I'm concerned about, right, is going to be the sum of these. It's ZL plus ZT2. And, okay, this is a J, right? J, so the J's are going to add. I've got 838 ohms of resistance plus inductive reactance of 2394 plus 838, which is 3232 ohms of inductive reactance. 3232. So this, now I know this, right? So the main three things I need to know are those three things. Now the V at the feeder end, I'll just call it V feeder, the sending end, right? Put a little line to neutral to remind myself it's a line to neutral voltage. It's going to be the current, so it's going to be the I times the Z total. So that's the voltage drop across the entire impedance, including the transformer, plus the voltage at the load reflected to that other side, which is well, that's the V, we could call it the V load line to neutral. Okay, so then I just plug in everything. So the current was 12 amps, negative 36.9, times an impedance of 838 plus J3232 plus a line of neutral voltage of 331.3. I could just say 331, it's close enough. Okay, now I just need to do the math. So the first thing I'll do is convert this to a polar form. So 838 squared, square root of 838 squared plus 3232 squared gives me the amplitude. So that's 33. So I'm going to have 12 times 3389. And then I've got to find the angles of everything. So I got negative 36.9. And then I'm going to have a positive angle if I take the inverse tangent of 3232 divided by 838. And that's 75.46 degrees plus 331 kV. So I'll just simplify that.
Isn't that 3339?
What is it? Let me check. I got 333. Oh, you're right. 3339. Yeah, my eyes didn't see it correctly. Thank you. Yes, 3339. I had 3338.9. There we go. 33 or 3340 roughly. Okay, so there we go. Is there any other mistakes, or does that look right to everybody?
Looks good.
Okay, great. Now I've got 40,000 volt drop. You say, oh my goodness, that is a lot. Well, compared to 300 kV, it's not that bad. It is bad. Remote communities suffer from this problem. But this is what's called a weak grid. Okay, so I got that voltage drop that I have to supply from the other end. And then the angle, but the thing is, a lot of it's reactive, so it's not going to really be as bad as it looks. So 75.46 minus 36.9 is 38.56 degrees plus 331 kV. Now I need to go and convert it to Cartesian again and sum these up. So I'm going to take 40 kV times the cosine of 38.56. And that is 31.278. Okay. 31,278 plus J 40 kV times the sine of 38. So that's 24,933 plus 331,000. So just add them up and then convert it back to polar form. 331 kV plus 31.278 kV is 36.3. This is actually my line to neutral answer. I'm going to keep the phase because I'm going to need it later. 362, 278. And then the angle, I'm sorry, no, it isn't quite. I have to get it to phasor. I'm jumping the gun. Plus J 24,933. Now I'm going to sum the squares up and I'm going to find the angles. So square root of 362, 278 squared plus 24,933 squared is 36,313. 363,130 volts RMS. And then the angle would be the inverse tangent of 24,933 divided by 362,278. Which is 3.94 degrees. Okay, so I've almost got the answer. The answer is that times square root of 3. B line to line at the ascending end is square root of 3 times 363,130. Which is 628,960 volts. So, if you get some people got like 1.2 megavolts or something. I don't know how on earth that they got that. And then there were other people who didn't do the transformation and they're getting something anywhere from 900 to 12,000 volts. You're way off, right? You know that the voltage at this transformer at this point has to be somewhere around 600 kV. So you have to use, you got to think about your answer. Does it make sense? 600 kV. It should be somewhere around there, and you're going to expect it to be higher because something had to be boosted up at the other end to even get 13.2 kV at the load end. Does that make sense? Or any questions on that?
My only question comes in is just because with my calculator I have it set up to do polarization on its own. So I typically do all these problems in polar. Is there a problem with just running through this whole thing in polar form?
Well, if your calculator is going to do what I just did, if you did it right, just if you program your calculator correctly, you could screw it up though.
I mean, the only thing I'm off by is I technically am off by a factor of less than 0.5% compared to your answer.
You can't add polars, okay? You were just lucky if you came close. You can't add polars.
No, I converted to rectangle. Mine does an auto conversion of rectangular, and then it reconverts.
Yeah, I mean, So,
okay.
As long as sounds like you programmed it correctly. I mean, maybe I rounded a few things, so it might be a little bit different in my answer, but
So if my answer is only off by like 0.05% compared to yours, that's well within reason.
Yeah, I mean, if somebody's if you're within, I would say, because I'm generous, if somebody was even within 5%, I would probably give them the answer. Now that is probably way off, but if you're 100% higher or 1,000% higher, then that's just doesn't make any sense, right? If there are rounding and things like that, it's I'd say within plus minus 1% on the final is a reasonable number. I'm not going to be as nice about that on the final. But yeah, I'd say within 1% is fine.
Okay.
And that's pretty reasonable. I mean, with engineering, you don't want to get like all hung up on 0.07%. I mean, that's actually bad engineering to try to get things to, the third decimal point. If you're within an integer of the right answer, or in this case, if you're within 1,000 volts of the right answer, you're well within a reasonable answer.
Okay.
Okay, now, is there any other questions so far?
So the reason we picked the base value is because you are mentioned they are reference to the transmission line, right?
Yeah. Yeah, I
So
gave
in
them to you reference to that transmission line, so that would tell you where to do your base.
Okay, so in the final you will now tell us the reference point, right?
Yeah, if I give it to you in per unit, I will always say with this, and if there's a transformer involved, I will tell you where it's referenced.
Okay.
You don't have to do any turns ratio transformations or anything now because of that.
Okay.
Okay, so the next step is to find. Now, I was very generous on this because I think no one did it right, but find the transformer. So we did A, right? We're going to do B. So if you're looking at your exam markup, which was kind of hard for me to do, and you say, oh, I'm way off, but he gave me credit. What's wrong with this teacher? Well, I'm just trying to be nice, okay? That's it. I understand. I'm trying to be fair because there were a couple of confusing things that happened during the exam. So I was fairly nice on B. Yeah, go ahead.
Speaking of that, where can I go to actually find that?
It should be up on, if you go up on to Canvas and click on your exam that you uploaded, it's marked up. So go to Canvas and you should see it. If you can't, tell me. I think.
Okay, I was looking at. Okay, now I see what it is.
Double and
Okay.
triple check that on everybody. Everybody should have it. If not, let me know. But you should see your marked up exam. There were a couple people that I had to do it offline because it was too much. There's something wrong with the file, and I think there's two people I need to send it to. I think it's Maxim and Shiraz. No, not Shiraz. Maxim and Kalila. I need to send them their exam. So FYI. Anyway. Okay. So let's go to the next one. Well, what we have to do is we're saying we're going on the other side of the transformer. So there's another impedance involved. Now we're going to move everything to the 4160 volt side of the transformer. So we need to know this is the voltage that the transformer is supposed to be putting out. This is what, the guy at the power plant's going to program his regulator to run at to get the voltage what he needs at the load end. And so there's the ZT2, but this up at a prime because it's moved to the 4160 volt side. And this is where, it's not a lot of work here, but no one did this. But it's still, you've got to pay attention to what you're doing here. So we know that the voltage and we know the current here. We know the current, let's start with that. So on the high voltage side, we had 12 amps minus 36.9 degrees. Now we're going to a step on the other side of a step up transformer. So the current is actually going to go up. It's going to go 600 divided by 4.16. And I'm taking out the 1,000-volt factor here. Or I could just say 600K 4160. I got to multiply that times that number to get the current. And then I know the voltage, it's this voltage here. Not that volt, it's this voltage here. So the voltage is 363.13 kV, 3.94 degrees. And then I need to find this. So this is probably the hardest part. If I found, I know that Z2, this is another reason why I was a little bit merciful on this, because even if somebody knew, we didn't really cover this much. It's in the section on per unit in the book, but I know that ZT2 on the high voltage side of the transformer is going to be the value I gave you, 0.02 times the base, which was 11.97 kilo ohms. But I have to, so I could find that. That would be 0.02 times 11.97. So that's 239.4 ohms. To 39.4. Now the way to
It should be CT1, right?
Should be what again?
CT1.
Yeah, that's
L2.
right. That's right. That's CT1. I apologize. Thank you. CT1. Now what I'd have to do the base conversion, I could do a turns ratio conversion. That's one way to do it. And I'm not 100% certain, just thinking myself, right? I'm saying to myself, do I know for sure, I could say, is ZT1 prime simply equal to, I know it's going to end up being a lot lower than the impedance on the other side, so I would be 4160. I don't even have to remember the formulas, but these are the line-to-line voltages. Now I know that I could do everything in the transformer, and some people tried to do that, but I guarantee if you do that, there's going to be a square root of 3, and it's going to screw up the answer somewhere. So it's going to cancel out. Now I think it cancels out here, and I think this is the right answer, times that. But there's a surefire way for me to know it. I believe that actually this is transforming it in ohms, right? Yeah, I'm getting everything to ohms. But I could also have said what's the base of the generator. If I can find that base, so I'll call this Z base prime, and then I could say that that base is going to be lower than the base of the transmission line, and I could say ZT1 prime is equal to Z base prime divided by the Z base of the transmission line. So this is the transmission line, this is the generator times the value that I got on the line side, which is ZT1. That's what I'm going to do. And so the S base of the generator is 25 megawatts or 25 MVA. The V base is 4160 divided by square root of 3. And the I base is the S base divided by 3 times the V base. So 4160 divided by square root of 3 is 24. It's about 2400. Come on, you dice. Froze up on me just a moment. What the heck? Hold on. I think I bumped something with my hand or my sleeve. Just give me a minute. I gotta go out of this. Man, this ticks me off. Okay. My pen is not responding. Jeez. Just waiting for it. I don't know what's going on.
Is that one of the Microsoft pens?
Yeah, I hate this thing, this Surface Pro, man. It's just, I'm gonna buy an iPad.
What you might want to do
Just stop working.
is it connected via your Bluetooth?
Yeah, maybe the battery died.
It's possible, or what you could do is you could try to, first thing I do when I have my Bluetooth devices and they desync is quickly kill your Bluetooth on your computer and then reboot it so it tries to resync quick.
Oh,
if you have the
yeah,
time.
I don't have time for that crap. Okay, we're going to type everything now. Sorry. 4160 divided by square root of 3. Damn it. Man, that's maddening. Because now I'm really going to be struggling to explain the other stuff to you. Okay. 2400 volts here. And then this is 25 MVA divided by 3 divided by the V base. So that's 3472 amps. Okay, so now the Z base is going to be equal to the V base over the I base. So that's 2400 divided by 3472. It's 0.69.
Could you zoom in? That's like hella tiny. You can barely see that. Thank you.
I'm really ticked off right now. Okay, so there it is. Now, the ZT1 is going to be equal to 239.4 times the ratio of 0.69 divided by 12. So it's really small, okay, by the 11.97 e to the 3. And I would expect that that's what I would have got here too. It might be the same number. In the interest of time, I'm not going to try to go check it. So 239.4 times 0.69 divided by 11.97 e to the 3 is 0.0138. Okay, so that's the impedance. Now the next thing is we want to find the circuit, and so we're going, we have this circuit here, so we know the current, we know everything, so we want to find the voltage at the transformer is the line of neutral voltage is going to be the current, which was did we find the current? 12 times 600 key, just to say I'll find that. 12 times 600,000 divided by 4160, that's 1730. So I have 1730 amperes. I've got an angle of negative 36.9 times 0.0138. See, this is going to affect it very little, but for all the work we did there, J90 plus the voltage, which was 360. Now this had, I got distracted. This has to be multiplied times the voltage ratio, 4160 divided by 600 e to the 3, right? So 363.13 times 4160 divided by 600 e to the 3 is 2511. 2511, there's a little bit of an angle, 3.9, okay? So, and then again, this is why, if everything had gone perfectly in the exam, this was doable, but that's why I let you guys have time on this. Now the volt, so if I can solve this, and the voltage drop across the transformer isn't a lot. It's 1730 times 0.0138. That's 23.87 volts. Okay, I've got that 90 degrees, and then plus the 2511, 3.9, and then convert everything to Cartesian. So the angle of negative 36.9 plus 90 is 53.1. And then I'm going to do 23.87 cosine of 53.1 is 14.33 plus J 23.87 times sine of 53.1 is 19 plus 2511 times cosine of 3.9 is 2505 plus J 2511 times sine of 3.9 is 170. And now I can convert this into the line to line by, I'll just do it in one step. I'm going to find the amplitude, square root of, so basically add 2505 and 14.3 together. Plus 19 plus 170 . So I got 2526 times square root of 3. And I get 4375 volts. That's what the transformer has to put out. Okay? Now I'm going to go quickly and do the next point so we can... problem 3 is pretty easy, but I confused everybody because I made a mistake. So I took responsibility for that. I'm going to try to clean that up. But number C was what's EA, right? So I can't draw the circuit because I lost my pen. It still doesn't work. I think the battery died again. So I got EA is going to be equal, since it's a generator, to the current that's coming out, the I. That's a phasor, times JXS, the synchronous reactance, plus the V line to neutral at the terminals of the generator. So you don't have to convert this to line or anything, it's just find that. So I gave you the XS up here. And it was, I think I gave it to you in ohms, 0.808 ohms. Okay, so I'm going to basically say EA, the line current didn't change, it's still 1730 negative 36.9 times 0.08 angle 90, and then I'm just going to use this right here. I'm going to just add that in there. So that was 2505 plus 1433. So 2519 plus J 170 plus 19, which is 189. And then I'm going to go ahead and solve this. It's just simplify that, 1730 times 0.08, which is 100, EA equals 138.4. And I'm going to end up finding the torque angle here, 90 minus 36.9, 53.1, plus 25.9, let's get the plus 25.19 plus J 189, and then go to the Cartesian, which is 138 times cosine 53.1 That's 82.85 plus 138.4 times the sine, 53.1 times pi over 180. That's 110.7. 2519 plus J 189. And then the final answer is convert it to polar again. So it's a 2610 approximately, with the angle, positive angle. It's a generator. I know I should have a positive angle, and I do. So I probably did everything right. Inverse tangent of the sum of 189 plus 110.7 divided by the sum of 82.85 plus 2519. And that's 6.6 degrees. And there you have it. Okay?